Well, thank you for coming in today. So this second lecture deals with the structural properties of solids. And since the entire series is about optical properties of solids, you might ask, well, why are we looking into the structural properties? And the reason is this slide, which I showed you earlier, that the electronic and vibrational properties of solids are derived from their structural properties, and therefore, in order to understand the electronic and vibrational properties, we should start with understanding the structural properties. I teach 2 semester-long courses at NMSU. I teach 1 class on X-ray crystallography, which is a semester long, and I teach another class which is on applications of group theory. So what I'm trying to do this morning is that I'm squeezing these 2 semesters into a single lecture. So I don't know how well that's going to work. Some of you will have seen this material, and then perhaps for those of you it will be a refresher in putting everything into the context that we need to understand optical properties of solids. If you've never seen this material before, then I hope that maybe it will motivate you to take a class and where you really study this material. And then, of course, as physicists, we have to be able to engage with topics in which we're not an expert. So maybe you will never take a class on group theory, but nevertheless, you still have to pretend that you know a little bit about it. So we will look at crystal structures, we will look at point groups and space groups, and we'll ask where are the atoms located, and we will classify optical vibrations, and we'll look at selection rules. And you're probably wondering, you probably figured out by now that I spent last weekend in Karlovy Vary, and you're probably wondering, what is this cup doing here? So we will get to that later. So what are the reference materials that you could use for this lecture today? You can start with a good text on solid-state physics. The undergraduate textbook in the United States at the bachelor's level is typically Kittel, solid-state physics. The graduate level text is usually Ashcroft and Mermin. There's a new book out that I haven't seen yet by Millie Dresselhaus. Part 3 of that book deals with optical properties, and that part is pretty good. I also have used David Snoke's book on solid-state physics. He was a postdoc at the Cardona group in Stuttgart, so he's sort of related to what I'm doing. I will show you why Nye's book is important. Rohrer is a material scientist, and therefore he looks at materials very different from physicists. Physicists always think about atoms. Where are the atoms located? How do the atoms move? Chemists think about bonds. And as physicists, we often think of the structural property of a material as a given. We don't worry where it comes from. We just say it's there. At least that's how I was taught. And therefore, reading Rohrer's book was absolutely fascinating, because he starts, well, what is the size of the atom, and how do the ratios of the ionic radii compare, and what are the bonding characters, what are the angles? And based on these properties, he gives a pretty good explanation why materials classify in certain structures. Symmetry is very important. And there is a new book by Dresselhaus, and that's the only book that I've seen which explains how to classify the lattice vibrations in solids. The book that I used last time I taught the class was Joshua, which is a little bit more readable than the old classic by Tinkham, which is from the 1960s, and it has more applications, especially related to magnetic symmetries. And then there's a number of reference volumes. The international tables, if you're dealing with material structures that are more complex than diamond or zinc blende or quartzite, which are more of the common semiconductor structures, then you really need the international tables. If you want to know what is the crystal structure of strontium ruthenate or some other distorted perovskite with a very unusual crystal structure, then you will find that in the international tables. The international tables are expensive, and they're a set of volumes which are this thick. One of my colleagues always has a copy in his trunk in case he needs to look up his crystal structure when he travels somewhere over the weekend with his family. And therefore, if you do not have access to the international tables, you can find a lot of similar information on the Bilbao crystallographic server, which is here. And sometimes you may want to plot nice pictures of a crystal structure for your for a paper that you're writing or for a poster or presentation that you're giving. And there is a program that you can use, which is very simple to use. And there you can plot crystal structures. And I will give you examples for all of that. So how many of you have heard of Emmy Noether? Yeah, a few of you? Well, Emmy Noether has, there's an interesting story behind her. She was the first woman in Germany to become a professor. However, because she was a woman, she did not get paid. That was about 100 years ago. And fortunately, things have changed. And the reason why things have changed is primarily because of a generation of women at that, women of her generation. So Emmy Noether has a theorem that for every symmetry of the Hamiltonian, there is a conservation law. So we can apply this in classical physics as well as in quantum mechanics. And if you think of standard classical systems, then there are 10 integrals of motion. So there are 10 conserved quantities in classical systems. So the first one is that if the Hamiltonian is not explicitly on time, if there are no time-dependent fields, then the energy is conserved because the time derivative of the Hamiltonian is 0. So that is very easy to see. If the Hamiltonian does not depend on position, then we have translational invariance. And because of the translational invariance, momentum is conserved. Rotational invariance, if the Hamiltonian can be rotated if the Hamiltonian is invariant to a rotation, if the Hamiltonian does not depend on the angle, then angular momentum is conserved. SO3 is the group of all rotations, and SO3 is the example of a Lie group. We will talk about what a group is a little bit later, but I just wanted to introduce here that SO3 is the group of all three-dimensional rotations. Prague is also a Kepler town, just like Regensburg and Linz. Kepler spent much time in Prague, and one of his books is called Harmonices Mundi, the harmonies of the world. And therefore, just like Noether, Kepler looked for the connection between symmetry and physical properties. If you think of Kepler's second law, then Kepler's second law is really a geometrical way of expressing the conservation of angular momentum. So these conservation laws here apply to three-dimensional systems like a hydrogen atom or a particle that's exposed to a spherical potential. Now, how do these conservation laws apply in crystalline solids? Well, first, energy is still conserved. excuse me, energy is still conserved if the Hamiltonian is not on time, if the Hamiltonian does not depend on time, so that is the same as in the classical case. However, in a crystal, translational symmetry is clearly broken because I have atoms, and if the distance, if I move the electron by half an atomic distance, then obviously that has a very significant impact on the potential that the electron feels. However, the crystal is periodic, and we will see that this periodicity of the crystal leads to a quantity which we call crystal momentum and leads to Bloch's theorem. The rotational invariance also does not exist in a crystal. We cannot rotate the crystal by an arbitrary angle and expect that it looks the same as before the rotation. Crystals have symmetries, but crystals are only invariant under discrete rotations with specific angles and are not invariant under an arbitrary rotation. And that leads to things like crystal field splittings and selection rules. Of course, symmetries are even more important in nuclear physics. If you think of quantum chromodynamics, the proton is made up of 3 quarks, and the spin of the proton is 1/2. So you think, well, that's easy. The proton is made up of 3 quarks, and each of the quarks has a spin of 1/2, and therefore, if 2 of the quarks are aligned with their spins parallel to each other, and the spin of the 3rd quark is aligned antiparallel, then together the total spin is 1/2, which is exactly what it should be to yield the spin of 1/2 for the proton from the 3 quarks. Unfortunately, this explanation is overly simplistic because we ignore that the quarks also have angular momentum, and we ignore that the quarks are bound together by gluons, which also contribute to the spin of the proton. So somehow there must be a symmetry leading to a conservation law which make the total spin of the proton exactly equal to 1/2. As we discuss the symmetries in a crystal, let us start with the translational symmetry of the crystal. The translational symmetry of the crystal is based on the Bravais lattice, which is a regular array of points, and the points are determined by primitive lattice translations, A1, A2, and A3, with integral coordinates n1, n2, and n3. Typically, one follows the convention that the primitive lattice translation vectors are arranged by increasing length, but unfortunately that convention is not always adhered to. The angle alpha is across from the primitive translation A. So these primitive translations together form a Bravais lattice, which has the properties of a group. The group properties means that the sum and difference of 2 translations is also a translation. We have a translation of 0 length, where all the coordinates n1, n2, and 3 are 0. For each translation, there is an inverse translation, which takes us back to the point where we started from. In addition, these translations also commute with each other. We can first go up and then left, or vice versa, and therefore these translations form an abelian group. It is very difficult on a mathematical point of view to deal with infinite crystals. And therefore, from a mathematical perspective, we assume that the crystal is finite, but then we introduce periodic boundary conditions. So if I have a large crystal here, I start on the left-hand side, and because the crystal is finite, there is a left-hand side, so I start here on the left-hand side, and then I move to the right, and then I get to the other edge of the crystal, to the right-hand side, and then I just assume that the crystal has somehow wrapped around, so if the electron comes out here on the right, it automatically re-enters on the left. That's known as the periodic boundary condition, and that makes this translational group a cyclical group. Once I have the Bravais lattice, I introduce a reciprocal lattice with these three reciprocal lattice vectors, which are perpendicular to the primitive translations in the direct lattice.
And the reason I am doing this is that I want to describe plane waves in the lattice, and that requires the introduction of the reciprocal lattice based on these primitive vectors which are given by the B's.
So if I introduce these reciprocal lattice vectors, then the complex exponential e to the I g dot t, so this is the reciprocal lattice vector times the translation vector. The exponential, the complex exponential of this scalar product is equal to 1. And that means that the reciprocal lattice describes all the plane waves that can occur in a lattice. And since electrons and phonons are primarily waves, we need this description, we need this reciprocal lattice so that we can describe waves in a periodic crystal. This construction here is known as the Brillouin zone. In the direct lattice, we usually deal with such regularly shaped cells, but that is only one way how we can cover space. There's another way, which is the Wigner-Seitz cell, which looks more irregular, and in the reciprocal lattice, we are better off using the Wigner-Seitz cell, and the Wigner-Seitz cell in reciprocal space is known as the Brillouin zone. So, since the translations of a crystal, since a Bravais lattice is a group, and similarly, since the rotations of a crystal form a group, we need to introduce the representations that these groups can form. The representation theory is another theory which goes back to Noether.
So, in this slide, I will try to explain what representations of groups are and how we use them in quantum mechanics. So let's suppose that we have a quantum mechanical system, like a hydrogen atom, for example, with a Hamiltonian H. Then we can look to solve the Schrödinger equation associated with this Hamiltonian, and that will give us the allowed energies. For each of these solutions, there may be not just one wave function, not just one electron that we can place at this energy, but this solution may have a degeneracy G, and there are one or more eigenfunctions, solutions associated with this energy. So for example, if we look at the state with angular momentum L equal to 0, then we can place 2 electrons there, including spin. If the angular momentum is 1, then we can put 6 electrons. If the angular momentum is 2, then we can put 10 electrons into this d orbital. So what the representations tell us how the eigenfunctions transform under a symmetry operation of the Hamiltonian. So for example, for L equal 1, we have three solutions corresponding to the three directions x, y, and z. And these are three different wave functions. Now, if we rotate the Hamiltonian, then somehow the solutions corresponding to this Hamiltonian will also transform, and that is what the representation tells us.
This is the original wave functions. This is the original wave function with L equal 1. And I rotate it, and then the result of that rotation is a linear combination of the wave functions of other wave functions with L equal 1. And in this case, these coefficients are known as Clebsch-Gordon coefficients, but we can do this quite general for any type of symmetry. So if I have an eigenstate, then the rotated version of that eigenstate can be written as a linear combination, and these coefficients here, that is called the representation. So there's various different ways of how a representation can be defined, but that's probably the one that we're most familiar with as physicists. The character of a representation is the trace of that matrix of coefficients. We can apply this theory of representations to the translational invariance of a crystal. And the question here is, what can we say about the wave functions for electrons or for lattice vibrations based on the translational invariance of the crystal? So I mentioned earlier that the translational group is abelian and cyclical. Because the group is abelian, all the irreducible representations are one-dimensional. That means for the translational group, I don't have to worry about this, about these complex coefficients. If I rotate a wave function, or in this case I have to say if I translate the wave function, because that's the symmetry we talk about, if I translate a wave function, I will get not a sum, but simply the same wave function multiplied by a complex coefficient. So that is an outcome of the fact that abelian groups have one-dimensional irreducible representations. The translational group is also cyclical because we introduced periodic boundary conditions, and therefore the phase factors are complex exponentials which look like this. So as an outcome of the translational invariance of the crystal, we can immediately see, based on the mathematical theory of representations, that the translated wave function is equal to the original wave function multiplied by e to the I k dot t, where k is a vector in reciprocal space. Another way to express the Bloch's theorem is that we can write an arbitrary wave function is equal to a plane wave part multiplied by a spherical part. So from the translational symmetry, we get this property k, which is called crystal momentum, and it is a conserved quantity. Now, when people talk about momentum conservation in solid-state physics, well, you assume momentum is conserved, right? You always assume energy is conserved, and we always assume that momentum is conserved. But in solid-state physics, we really mean not momentum, but crystal momentum. And there is a difference between momentum and crystal momentum. The vector k and the vector k plus g, obviously they're related to different momentum, but they have the same crystal momentum, because this e to the I g dot t is equal to 1. So translating a vector in reciprocal space by a reciprocal lattice vector, that translation does absolutely nothing. So we always have to consider the fact that k can be shifted by a reciprocal lattice vector, and that in that case crystal momentum is still conserved, and such a process would be called an Umklapp process. So we've talked about translational invariance, so let's continue with the rotational symmetry. Not every rotational symmetry is compatible with translational invariance. So for example, 5-fold and 7-fold symmetries cannot occur in a real crystal. The only rotational symmetries that are allowed in a crystal are 0 or 360 degrees, and then we can have 6-fold, 4-fold, 3-fold, and 2-fold rotational axes. So n is 1, 2, 3, 4, and 6, and then we can have a rotation by 2 pi over n. So remember that the rotational matrices about the axes x, y, and z are given by 3-dimensional matrices like that. So how do we prove that only these type of rotations are allowed? And there is a very nice proof in Tinkham's book on group theory. So let's call the axis of rotation, let's call that z. And then we rotate about the z-axis with an angle 2 pi over n. And we want to show that for this rotation, n must be 1, 2, 3, 4, or 6. And this proof goes in 2 steps. So first, we want to show that there is a translation vector in the xy plane. There's a translation vector of the crystal in the xy plane, which is then perpendicular to the z-axis. So we assume that T is an arbitrary translation vector in the Bravais lattice, and then T prime and then T prime, which is the rotated translation vector, that's also a translation vector. That is an outcome of the rotational invariance. Because the Bravais lattice forms a group, the difference T minus T prime is also a translation vector. And if we do this difference, if we calculate this difference, then in that difference, the x components of these vectors cancel out, and therefore this difference is perpendicular to the z-axis. So we've shown that yes, there is indeed a translation vector in the Bravais lattice which is perpendicular to the z-axis. In the second step, we assume, so here now the rotational axis, we rotate about this point, the axis comes in and out of the plane. So now we have a translation vector which is perpendicular to that axis, so it is in the plane, and there's obviously many of these translation vectors. And let's just assume that R is the shortest of these translation vectors. Since there are many, but a finite number, we can pick the shortest one. So this here is the shortest one, and then we take the shortest translation vector and we rotate it by one of the allowed rotational angles, and then we get this vector R prime. Well, R prime now must also be a translation vector, and the difference between R and R prime also must be a translation vector. So now we assumed that R was the shortest translation vector, and therefore R minus R prime cannot be shorter than R. If we look at geometry, then this distance, the length of this vector R minus R prime, is 2r times the sine of the half the rotation angle, and that must be greater or equal to the length r. So this distance must be greater or equal than the length of r, because r was assumed to be the shortest vector. And in order for this to be true, n must be less than 6. And then there is a specific case with a 5-fold symmetry. And for that, we have to draw a specific picture, which is also in Tinkham. So we need a specific argument to exclude 5-fold symmetries. And therefore, the only allowed symmetries are 1, 2, 3, 4, and 6. Sometime in the 1980s, there was a big hype because people found 5-fold symmetries in a crystal, which is obviously not allowed. And microscopic examinations of these materials which produced 5-fold symmetries in the electron and X-ray diffraction showed that these were not actually periodic crystals, but somehow the crystal consisted of domains which are oriented in such a way that it produced 5-fold symmetries. So quasicrystals are not periodic crystals in the same sense as the Bravais lattices that we're talking about here. Since the rotational symmetries are limited in a periodic crystal, this also limits the crystal families or crystal classes that we can find. And I don't know to what extent you can read this. Probably, maybe if you're sitting up front, you may barely be able to read this. So I apologize for that. It's not the best resolution. So in a cubic crystal, I have 3 perpendicular 90-degree axes. In a tetragonal crystal, and all of the lengths are all the same. In a tetragonal crystal, I still have 3 4-fold axes. I have 2 4-fold axes because the cube has been stretched along one direction. So one of the 4-fold axes disappears. And if I go to a monoclinic system, then in a monoclinic system, in an orthorhombic system, which is here, in an orthorhombic system, I still have 3 right angles, but the length of the 3 axes are all different. Then there is a hexagonal system, which is here, which has 1 6-fold axis. And then there is a triclinic system, which has no rotational symmetries at all, because there are no right angles and there are no axes of the same lengths. And then there's the monoclinic structure, which I think is this one, where I have 2 right angles, but the 3rd angle is not 90 degrees. So these are the 6 or 7 crystal systems. Sometimes the hexagonal family is sometimes broken up into 2 systems, which are called trigonal and hexagonal, and they're somehow related or can be made related. So that's why there's a question, is it 6 or is it 7? So obviously, this here is the cell of a cubic system, the cell for a cubic Bravais lattice. So let's put another atom in the center. And this body-centered cubic system still has many cubic symmetries. We can rotate it by 90 degrees and it turns into itself. But The crystal cell that belongs to this new type of crystal where I put an atom in the center of the cube, the unit cell for this crystal actually looks like this, and it is very, very complicated. It does not have any right angles. So if we are only looking at the unit cell for this BC structure, then we do not see the cubic symmetry in this unit cell, even though this strange unit cell allows 90-degree rotations. The same is true if we put atoms at the faces of the cube. Then the unit cell is formed by these primitive translations. And you can see the scalar product between A1 and A2 is non-zero. So obviously the angle between A1 and A2 is not 90 degrees. So we do not see quite easily in this representation with these primitive lattice vectors that this crystal has, that this lattice has a 90-degree rotational symmetry. We only see that in this representation. So whether we use this primitive cell or this centered cell has several considerations. If we look at the face-centered cubic Bravais lattice, then we see that we have 5 lattice points per cell. There are 8 lattice points along the corners. Each of these points belongs to 8 cells, and therefore this point here really counts as 1/8. And in addition, we have we have 6 faces of the crystal, and each of the points belongs to 2 cells, so that's 6 times 1/2, so that's 3 crystal points are sitting on the faces along with the one at the corner, so that gives us 4 lattice points per cell. So we can either use the primitive cell, which has only 1 lattice point per cell, but we do not see the symmetry of the problem in the primitive cell, or we pay the price of building a larger cell with more points per cell, but then we easily see the cubic symmetry. So that is always a question whether we want to work with the primitive cell, which is has a lower symmetry, or whether we want to work with a higher symmetry but then have more points per cell. If we take into account, so we said before that there are 7 crystal systems, which are these, and then we need, but some of these can allow centering. And therefore, there are 14 Bravais lattices. And the letter P means that the Bravais lattice is a simple lattice where there's really just the 4 points, just the 8 points at the corners. The letter I means that this is a body-centered cell. The letter F means that it is a face-centered cell. Where are we? Cubic. Here's the face-centered cell. And then there's also the base-centered cell in the orthorhombic or tetragonal case, where there's an atom at the base, but not here on the other 4 faces. So from the 7 crystal systems, we get 14 Bravais lattices if we include centering. So far, we've only talked about Bravais lattices. And the lattice itself is not a crystal. It is just a mathematical construct, an abstract construct. From a Bravais lattice, we get to a crystal structure if we define a basis. So the basis means that I have 2 atoms here, a blue one and a red one, a large one and a small one, and I place these two atoms at each of the points in this Bravais lattice, and that gives me a crystal. So I need to specify, to completely specify a crystal, I need to specify not only what are the lengths and angles of the primitive cell, I also need to specify where are the atoms located relative to the Bravais lattice points. So I need to specify the coordinates of the atoms within the cell, and these coordinates are usually referred to as Wyckoff positions, and I will give you a table. I will tell more about the Wyckoff positions later. So once I have the Bravais lattice and the basis, I can ask what are the symmetries of this new crystal. And it turns out that there are 230 specific space groups which define the symmetry of a crystal. There's exactly 230. And the symmetries of this crystal include rotations, mirror reflections, the inversion. An inversion followed by a reflection is called there are combinations of these. And of course, there are translations. So there's 230 space groups which leave the various crystals invariant. If I set the translations equal to 0 in these 230 space groups, I'm getting 32 point groups which only include those symmetry elements where the translation has been set to 0. So if I don't worry about the translations, I have to worry about much fewer point groups. So what I will do now is I will show you examples of crystal structures that are becoming more and more complex. So the first question we can ask is, are there any real crystals which have a basis that consists of only one atom? Well, obviously that must be an element because I have only one atom. And there are quite a few elements which have just one atom per Bravais lattice cell. And these are the BCC metals and the FCC metals. A BCC metal is, for example, iron or chrome, where I have chromium atoms sitting at the corner and another chromium atom sitting in the center of the cell. So chromium is an element with just one atom per Bravais lattice cell. And then the FCC metals, there's many more metals like aluminum, copper, gold, lead, nickel, platinum, silver, etc., that crystallize in this FCC structure. Similar to chromium is the cesium chloride structure, where I have one atom sitting at the corners and another atom sitting at the center. But in chromium, these two atoms were the same, and therefore it was a BCC structure. In cesium chloride, I have two different atoms. Therefore, the cell here is simple cubic, and I have one atom at the origin and another atom at the center of the cell. That's the cesium chloride structure. The sodium chloride structure is FCC with one atom at the center and one atom sitting here shifted by half a cubic length along one of the axes. So the NCl structure has two sublattices. There's an FCC-like sodium sublattice and a FCC-like chlorine sublattice, and the two of these sublattices are shifted by half a cubic length. And the third cubic example that I want to show you is the diamond or zinc blende structure. And it's very similar to the sodium chloride structure. It is also FCC, but now instead of having the second atom shifted along a cubic axis, In this case, the second atom is shifted along the body diagonal by a quarter of the body diagonal. So you see here that I'm writing this as an atom with, as a cell. I'm writing this crystal structure as a Bravais lattice with two basis vectors. Remember, for an FCC lattice, we have the primitive cell or the conventional cell. If we choose the primitive cell, then indeed I have only two atoms in the primitive unit cell, but that's not typically how I will write this. I will typically choose the cubic cell, but then I have to say, well, in addition to these, I don't just have these two basis vectors, but I have 4 pairs of sodium and chlorine atoms because it is an FCC structure. It is an FCC structure where I have 4 lattice points per cubic cell, per conventional cell. So I have 4 pairs of these sodium and chlorine atoms. So I'm writing plus FCC. That means I have these 2 times 4. The other question, in the zinc blende structure, carbon, silicon, and germanium form the diamond structure where the blue atoms and the red atoms are the same. 3,5 compounds or some 2,6 compounds form the zinc blende structure where these two, where the blue and the red atom are different. When I do calculations for such structures that have a basis, it is very important to specify where I put the origin of the coordinate system. There is something which is called the point origin, where either the cation or the anion will be sitting at the origin. So that will be point origin. But I can also put the origin here at the center between the two atoms. And that is more symmetric. And that can be a center of inversion. And that is called the conventional origin. So when you look in the international tables, you will see conventions for both origins. While they are equivalent, they do have a significant impact on what exactly the symmetry operations look like. So these are only 3 of the cubic structures, but there are literally, dozens, maybe hundreds of crystal structures. And there are a number of standard structures. And there is something which is called Strukturbericht, structure report. And these are some of the more common crystal structures that are listed in the structure report. And a structure that starts with the letter A is an element. Structures with B and C have 2 different elements, D also, but it is more complex. And then E has 3 or more different atoms in the structure. So for example, there is titanium disilicide or titanium dioxide. Those are C structures. Sapphire has is a more complex structure, starts with a D. And a perovskite, like calcium titanate, starts with an E. Spinel is even more complex and starts with an H. So this is called the Strukturbericht notation. And Rohrer is a very good book which discusses many examples here. And the examples that I'm showing you are taken from Rohrer's book. So we need to start with, well, what is the material that we're dealing with? Copper, tungsten, magnesium. So we call that the formula unit. What is the space group of that crystal? What are the dimensions and angles? So since this is an FCC structure, there's only one parameter that we need, that is the lattice constant. It's the same in all three directions, and the angles are all 90 degrees. And then I have 4 of these copper atoms, so there's 4 formula units per conventional cell. And where are they located? These atomic positions, I called them the Wyckoff positions earlier. So in this simple case, I put copper at the origin, and then I need to replicate it 4 times as given by the FCC prescription. This is a typo. This should be BCC, of course. So that's another example. The hexagonal close-packed structure has 2 formula units. So for example, magnesium is a metal which crystallizes in the hexagonal close-packed structure. There's 2 different close-packed structures, the FCC and the HCP. So the HCP is has 2 atoms per unit cell, so the formula unit is magnesium, and then I have 2 formula units, and because it is hexagonal, I need to specify 2 dimensions, the A lattice constant and the C, the vertical lattice constant, the in-plane and the out-of-plane lattice constants. And I have a space group and 2 formula units. And because I have 2 formula units, I need to put the magnesium in 2 different positions. 1/3, 2/3, 1/4, 2/3, 1/3, 3/4 along these axes. So using these Wyckoff positions, I have specified my basis, and therefore I have uniquely defined what the crystal looks like. So we've already seen this slide. There are many, many of these structures. And the reason why we classify the different materials with these structures is that once I understand one structure, like the rock salt structure for sodium chloride, there's many, many materials which have this sort of structure. So I think we're continuing now more with the symmetries. The structures that we've looked at so far here on this slide, they all had relatively high symmetry structures, high symmetry properties. But not all materials crystallize in cubic or hexagonal structures. Some have lower symmetries. And therefore, we need 32 point groups to describe the symmetry properties of crystals. And the symmetry properties we can have, I've mentioned those before. We can have an n-fold rotation. We can have the inversion. And then there's 3 types of mirror planes. There can be a vertical mirror plane, a diagonal mirror plane, or a horizontal mirror plane. A symmetry group that starts with a D is a dihedral group where I have 2 rotational axes that are perpendicular to each other. So I might have a 4-fold rotation along the z-axis, and then I have 4 2-fold rotations which are perpendicular to the highest symmetry action. S is a rotation followed by a inversion, or a rotation followed by a mirror reflection. So that's called an improper reflection, Spiegelreflexion. So that's where that S comes from. And finally, the highest symmetry groups are the tetrahedral and the cubic symmetry group. You know what a cube looks like. This is a tetrahedron. And a tetrahedron has many of the same symmetries as a cube, but it lacks that inversion symmetry that we see in a cube. So these symbols here are called the Schoenflies symbols, and we can use the Schoenflies symbols to enumerate the 32 point groups. There's also another system which is called the international notation to describe crystal symmetries, and here The letter N is simply an n-fold rotation. M is a mirror plane. If I have an N with a bar on top of it, then that's a rotation followed by an inversion. And N dash M, or N over M written as a fraction, is a mirror plane which is perpendicular to the n-fold rotational axis.
Excuse me, what is an improper rotation?
An improper rotation. So the question is, what is an improper rotation? So a rotation is I rotate, right? But I can also rotate and then I can flip. So that's what the improper rotation is. Instead of using these numbers, some people prefer pictures. And I was never very good at art in school. And therefore, I will never be a good crystallographer because my brain only works in 2 dimensions. I can try to work with formulas. I can do abstract math. But if art had been a required component of our science curriculum, I would have become a linguist. So some people like pictures more than they like formulas. I'm not one of them, but there certainly are graphical ways of representing the crystal structures, and therefore there are these what's called stereographic projections of the 32 point groups. So there's 32 point groups in which the translations are all 0, and there's 230 space groups. And 73 of the space groups are symmorphic space groups, and that means that the point group is a subgroup of the space group. So what that means is that if I rotate the crystal, I don't have to translate it at all. There's no symmetry elements where I must follow up on the rotation with a translation. If you look at this example here, so you have these locomotive engines, and the lines here, that is the lattice constant, and I can translate the crystal by the distance between 2 of these locomotives, and assuming that this goes on infinitely. So I just move this engine, I move it here, and this one I move it here. So obviously this thing has translational symmetry. But in this picture, below the plane, there are also locomotive engines below the plane. So obviously, there is some sort of a mirror symmetry. But if I do the mirror symmetry, if I flip this piece of paper upside down, I have to shift it by half a lattice, by half a lattice vector. So the non-symmorphic space groups have glide axes, glide planes, and screw axes. So this is what's known a glide plane. There is a plane of reflection, which is this plane, and I can flip. But if I flip this thing upside down, I have to shift it by half a cell length. So that's called a glide plane, which is a reflection followed by a non-primitive translation. And one example is the diamond crystal structure. So if we assume that this is diamond, then the blue atoms and the red atoms are the same, and they're all carbon atoms. And I'm using the point origin, and the diamond crystal has inversion symmetry. So the origin is located here, and now I operate the inversion on this crystal. So what will happen? This red atom will move here. So obviously, if I use the point origin and execute the inversion operation, then the crystal looks different. but then I shift the crystal, I glide along the body diagonal by a non-primitive translation, which is 1/4 of the length of the body diagonal. And then the crystal will look exactly the same as before. So in the diamond structure, the inversion must be followed by a glide. And therefore, the diamond structure has a non-symmetric space group. This is the other example of the types of elements that I have that are non-trivial and have combinations of a rotation and a translation. I have a threefold axis in this structure. I can rotate by 120 degrees, and you can see easily that a 120-degree rotation will leave this picture invariant. But now let's assume that the red and blue atoms are the same. And then I can also rotate, but then I must follow up with a translation by half a repeat length. So I rotate and I shift, and that is known as a screw axis. So together with the screw axis and glide planes, I'm getting these 157 non-symmetric space groups. And you'll have to stare at these pictures for a while and try to understand what this actually means. And then, since there is a very large number of these space groups, that's why you always must carry a copy of the international tables in the trunk of your car, right? Like my colleague does. So in the international tables, it's a thick book with a few hundred pages. You find all of these 230 space groups. And the first question is, well, what notation do I use? And the most common notation is not very original, not very imaginative, because you simply number the space groups from 1 to 230. And so you need to memorize what number is associated with the crystal structure that I have in my lab right now. Number 167. This happens to be lanthanum aluminate, so that's a distorted perovskite. So that is one way of classifying space groups by simply numbering them. Another way, for every space group, there is one specific point group. So for example, for space group 167, the point group is D3D, so it's a D group. I know that it has orthogonal rotational axes, and there's a threefold axis, and there's a diagonal mirror plane. And then there's a superscript 6, so this is the 6th space group, which belongs to the point group D3D. So this is related to the Schoenflies notation for the point group. This is the international rotation, the international notation for space groups. So it starts with an R, and that means that it's a rhombohedral space group. 3 bar, so there's a threefold axis that's somehow related to a mirror plane, and I forgot what the C means. So these are the various notations that we use to describe the space groups. There is a graphic way to explain all the symmetry operations and the especially the non-primitive translations that go with the operations in the point group. So this can be quite complicated. So in addition to this graphical representation, you find in the international tables also the the matrix operations for the symmetries. There is usually a table which gives you the systematic extinctions in X-ray diffraction. So if you have a crystal with this space group, which X-ray reflections are automatically missing? So that is good to know. And these are the Wyckoff positions. So for lanthanum aluminate, I can put the, there are A, B, C, D, E, F. So there are 6 different positions in the lattice with different symmetry properties. And if I know from the structure, so this is sodium chloride, I have 4 atoms in the A position and 4 atoms in the B position. That does not tell us anything. What we need to do, there's 4 atoms, there's 4 chlorine atoms in the A position. We need to go to the crystallographic tables and we see A position. What does that mean? Ah, that means I have an atom at 0, 0, 1/2 and 0, 0, 3/2. So the Wyckoff, the international tables tell us where the atoms are located in the unit cell. And by the way, I often get papers for review, and then they talk about some structure, and I have never seen this structure before. I'm not familiar with this material. It is a great help to me as a reader of an article if you tell me what is the space group, what are the symmetries of this structure, and where are the atoms located. Maybe a picture would help as well. So typically, this is something that I like to see in articles rather than having everybody assume that everybody knows what this material is. So if you cannot get access to the international tables, there's also the Bilbao crystallographic server. And much of the same information can be found in the crystallographic server and much more than what's in the international tables. So for example, here in the crystallographic server, in the Bilbao server, you find the Wyckoff positions for all the 230 space groups. You find the character tables of the point groups and the space groups. And you find the Brillouin zone. So sometimes, so let's say you find a paper about a band structure for lanthanum aluminate, and they have given you a band structure diagram, but without knowing what the Brillouin zone looks like in lanthanum aluminate, the band structure picture itself can be rather difficult to understand. There is also a very good paper, which I'm giving you here at the bottom, which lists the Brillouin zones for all possible materials. So much information can be found not only in the Bilbao crystallographic server, but also in the, not only in the international tables, but also in the Bilbao crystallographic server. Nye is a very good reference volume, because if you have a crystal, then you're interested in what are the properties of this crystal. If I apply an electric field, how will the material deform? So that will be a piezomechanical property. If I apply an electric field, what is the dielectric displacement? So I do ellipsometry, D is equal to epsilon E. I apply an electric field and I'm measuring the response. So I'm interested in the dielectric tensor. So for an arbitrary crystal structure, this epsilon is not a number, but it is a tensor. It's a first-rank tensor with 9 coefficients. Do I really need 9 coefficients, or are some of them equal to each other? Are some of them 0? In the cubic case, that is simple. In the cubic case, there is only one number, so the dielectric tensor for a cubic structure, the off-diagonal elements are 0 and the on-diagonal elements are all equal. So in Nye's book, you find for all 32 space groups, for every crystal class, you find tables like this which tell you the symmetry properties of the tensor. So for example, lanthanum aluminate is this crystal class here, 3 bar M. This is the symmetry of the dielectric tensor. The off-diagonal elements are all 0. These two elements are the same, and the third one is different. So with two numbers, I can describe the dielectric tensor in lanthanum aluminate. This here is too small to see, but this is epsilon and this is sigma. So what is the relationship between the stress sigma and the strain epsilon? So this here is the elastic tensor with 36 components. And again, you see exactly which of these 36 components are 0 and what the relationships are between the other properties. So this is in the appendix of Nye's book, and the exact reference was on one of the earlier slides. I have a few more examples, and if we get to more and more complex structures, so this is rutile, so this is titanium dioxide. So I have one titanium atom and 2 oxygen atoms, and here are the Wyckoff positions listed. And the titanium is easy. The titanium sits at one corner of the tetragonal cell. I think it's tetragonal. Yes, it's tetragonal. So one titanium atom sits at the corner of the tetragonal cell, and the other atom sits in the center. But the oxygens, you see it sits at XX0. So the position of the oxygen atom in rutile depends on this internal parameter X. So for titania, it is not sufficient to just list the unit cell properties. You also need to know this parameter X, the internal parameter, in order to completely specify the structure. Spinel is a beautiful gemstone. It's incredibly complicated because there are 7 atoms in the formula unit, magnesium, 1 magnesium, 2 aluminums, 4 oxygens. So there's 7 atoms in the formula unit, and then I have 8 formula units per cell, so I have 56 atoms per unit cell. So it's quite a complicated structure. And another example is perovskite, strontium titanate, as an example of a perovskite. Perovskites have been has become of interest recently because instead of putting strontium here, you can put an organic molecule, and some of these perovskites with organic molecules make very good solar cells. And again, you see there's a huge number of perovskites crystals. How do you draw? How do you draw pictures like that? My students told me about a program called Vesta. So I downloaded it yesterday afternoon, and I had never seen it before, and it took me about an hour to draw this picture here for strontium ruthenate. So the program is not difficult to install. This is the website where you install it. And then once you have installed the program will ask you for a file which has information about your crystal structure. And there are various different conventions. The most common one is this one, CIF. So if you do a Google search for strontium ruthenate crystal structure, then it will give you a whole bunch of websites which have the CIF file. There's a Springer materials database. And then you download the CIF file, you open it in Vesta, and then it immediately pops up with this picture which shows you what the crystal structure looks like. And in the CIF file, well, you need to give it the position, you need to give it the cell parameters, the lengths and angles, and you need to give it the Wyckoff positions, and that gives you this structure. Here you have 5 atoms per formula unit and 4 formula units per cell. So this cell is about 4 times as large as the regular cubic perovskite cell. Do you have any questions so far? Yes?
I missed this point maybe. So if I have a compound and I want to know all these parameters for the compound, this lattice constant and alpha, beta, gamma and all of this, which database should I go?
So the question is, if you have a compound and you want to know what are the cell parameters for that compound, how do you find the parameters for that compound? So what I do is I just do a Google search. I do a Google search, and I have not found many errors in Wikipedia. Wikipedia is usually a very good source, even though academics frown on Wikipedia because it is not peer-reviewed. But I usually rely on Wikipedia, at least to make myself clear. I try to understand something based on Wikipedia, and then I go to the peer-reviewed literature and see whether it agrees, and it usually does. So a Google search, and when I looked for strontium ruthenate, I found a Springer materials database, but I just found that on Google. There's other ways to find that as well. So I would not recommend one specific materials database. Yes?
You have mentioned symmetry group with reflection and light, and as an example, we have mentioned diamond structure. But if you copy a face-centered cubic structure, but by one force vector, then you need just pure glide, no reflection. I cannot see any reflection.
So the question is about the diagonal glide.
Is it possible that symmetric space group could contain groups without reflection with pure glide, or symmetric group is a definition for reflection and glide? Because if you can see these red balls, then they are formed by shift. By one fourth position from 0, 0, 0. That means a face-centered cubic is copied by one fourth vector, and I cannot see there any reflection. Just pure shift of face-centered cubic.
So, if you can, so the question has to do with the relationship between the translations and the rotations in a crystal, right?
Concerning to definition of symmetric space group, because if diamonds, the structure belongs to symmetric group, then the definition of symmetric space group, as you have mentioned, is not precise, because you have mentioned that there is reflection followed by translation, but the diamond structure can be obtained by pure glide, by pure copy of face-centered cubic crystal to new position given by vector 1 force, 1 force, 1 force. You understand me?
I think I understand. So the diamond structure is definitely a non-symmetric space group, because the international tables tell us. So there's no question about that. So what does that mean? Non-symmetric means that there are some point group elements which do not leave the crystal invariant. That is the definition of a non-symmetric space group.
That means this picture does not correspond to definition of symmetric group. Yes.
This example here shows us a non-symmetric group because it defines what a glide plane is. So in this example, a mirror reflection by itself is not a symmetry operation because it does not leave this picture invariant. A mirror reflection must be followed by a translation, which is not a primitive translation.
But in the diamond structure, there is no reflection followed by translation. There is just pure translation.
In the diamond structure, the distance between the blue and the red atoms, this is not a translation that is a part of the Bravais lattice, and therefore 1/4, 1, 1, 1, that is a non-primitive translation. It does not belong in the Bravais lattice.
Okay, understood. But every point from this set of red balls or red atoms could be obtained by pure translation A/4 times 1, 1, 1, as you have mentioned.
The blue points form a Bravais lattice, and the red points also form a Bravais lattice. But the diamond structure consists of two interpenetrating FCC lattices shifted by this vector, and therefore, because of the inversion symmetry that I have in the diamond structure, I can go from one sublattice to the other sublattice, and if I do that, then I need the non-primitive translations.
That means this definition is concerning just two Bravais lattices, the simplest crystallographic structure as can be possible, and not, for instance, face set with cubic as we can see. Correct?
I did not follow. Maybe we can continue this afterwards, okay? The application that is most important to me for group theory in solids is the classification of the lattice vibrations. So I'm interested in Raman spectra, and I am interested in infrared ellipsometry of materials. So if you have an arbitrary material, strontium ruthenate, let's say, and you do a Raman experiment, which atomic vibrations in this lattice would you expect to see in a Raman spectrum? And what type of reflections, what type of peaks would you expect in an infrared ellipsometry spectrum? And in order to answer this question, we need to look at the character table of the point group. And in this character table, you will find the list of possible representations. Remember, what is a representation? A representation tells us what type of degeneracies are possible and what type of symmetries do the wave functions have that belong to the eigenspace for a specific energy state. So I have 1, 2, 3, 4, 5, 6 representations for this symmetry group, and the character table also tells us how the basis functions, how the eigenfunctions belonging to these representations, how do they transform. So this is a one-dimensional representation. It transforms like Z, and this is a two-dimensional representation, and it transforms like X and Y. So if a representation transforms like x, y, z, then that looks like a vector, it transforms like a vector, and therefore these are the infrared vibrations. Representations that transform like binary products of the coordinates x squared, z squared, xz, yz, etc. These binary polynomials, second order polynomials of the coordinates, they tell us the Raman modes. So what we need to do is we start with the crystal structure, and then somehow we need to sort the normal modes of the crystal by representations. And then if once we've done that, the character table will tell us which of these are Raman active and which of these are infrared active. That is described in the book by Millie Dresselhaus. So we have n atoms per primitive cell, and therefore this crystal has 3n degrees of freedom. It is much easier to do this analysis with in the primitive cell rather than in the conventional cell, because that reduces the number of atoms that we're dealing with. So there are n atoms per primitive cell, gives us 3n degrees of freedom. 3 of these degrees of freedoms are translational degrees, and those are associated with acoustic phonons. And then there's 3n minus 3 optical phonons. So now we want to find the representations for these optical phonons. So here's what we do, how we do this. So we start with the Bravais lattice and the basis, and we need to know the point group and the space group. And we have to somehow find that in the literature. And we need to know the Wyckoff positions, and that means where are the atoms. The international tables will tell us the site symmetry of the Wyckoff positions. So the international tables will tell us how the atoms move under certain symmetry operations. We call NR the number of invariant atoms for a symmetry operator R. So let's say R is a mirror reflection, and I have 10 atoms in the unit cell, and I perform that mirror reflection, and 3 of these atoms are sitting on the plane, so therefore these 3 atoms will be invariant. The other 7 atoms are not sitting on the plane, and therefore they will move. So this NR is equal to 3, so that's the number of atoms which are invariant for a specific mirror reflection or rotation or inversion, etc. So that is NR, and in here R is the symmetry operator, so I'm taking the determinant, I'm taking plus or minus 1, the determinant of the symmetry operator, plus 2 cosine phi, where phi is the angle of rotation, and I'm calculating this expression for every symmetry operator. And this expression defines a representation, but it is a rather large representation because the dimension of this operation, the dimension of this representation is very large. So using characters, I can decompose this representation into irreducible representations. All I need is the character tables. And then once I've done that, then I will know which of these representations, irreducible representations, belong to Raman active or infrared active phonons. And it is not that hard. It takes a couple of weeks if you do this for the first time. when I teach the group theory class, then that is usually one of the final projects that I assign to the students at the end of the semester. So this is what we need to calculate. And lanthanum aluminate and spinel, so these are two different compounds where we performed infrared ellipsometry measurements. And then my master student calculated these representations. And you see here for lanthanum aluminate, the A1G and EG modes. Those are Raman active modes shown in blue. And there's A2U and EU modes. Those are the infrared active modes. And then there's also an A1U and an A2G mode. And those are silent, and therefore they do not show up in first order Raman or infrared spectroscopy. And you can do the same for spinel. And again, the blue modes here are Raman active, and the red modes here are infrared active. So with this classification, that tells you what type of modes to expect. And if you want to go deeper, then you can also find the normal modes. How do the atoms move under these operations? Okay. So now I want to do something completely different. Because so far, the first application was that we looked at how do we calculate the lattice vibrations? How do we find the Raman active modes and the infrared active modes? But in addition to the lattice vibrations, we also have to worry about the electronic structure of a material. So in what time I have left, I want to talk about the electronic structure. Many textbooks will tell you that the spin in quantum mechanics is a purely relativistic effect because it is derived from the Dirac equation. It is true that the Dirac equation gives you the spin, but you can also find the spin purely without knowing anything about relativistic theory. We do not need the Dirac equation to know that there must be spin. And even in non-relativistic quantum mechanics, there is a perfectly good argument how to introduce the spin. And the key to this is in pure math. I always tell my students I don't do math. And what I mean by that, I don't do equations. I particularly don't like to solve differential equations. But my first job was actually being a teaching assistant in the mathematics department in Regensburg in linear algebra. In Regensburg, the physics students did the first year math courses together with the mathematics students. And therefore, we had to learn quite a bit of math, especially abstract math. And one of the courses, one of the upper division electives that I took was a course on Lie groups, which has really influenced my thinking about quantum mechanics. So there is this mathematical theorem. The finite dimensional projective representations of a compact Lie group are identical to the representations of its universal covering group. If we understand this theorem, then we can introduce the spin in quantum mechanics without needing any relativistic theory. And I will want to take a few minutes in giving you some background, some hand waving. According to Niels Bohr, truth and clarity are mutually exclusive. I don't complain that I understand this myself. And I certainly could not prove this theorem, but I can make some hand-waving arguments, and I can try to maybe make this statement a little bit clearer. I talked before about representations. that the representations tell us how a wave function transforms under a symmetry operator. But this description, this definition of a representation is too restrictive for quantum mechanics, because two wave functions describe the same state in quantum mechanics if they only differ by a phase. So I have a wave function psi, and I have another wave function which is different by this complex factor r times e to the I phi. R is the magnitude and phi is the phase of this complex number. Obviously, these two wave functions are different, but the quantum mechanical states that belong to these two wave functions are the same. So therefore, I need to introduce an equivalence relation that I'm calling two wave functions identical if they only differ by a complex phase. That changes the definition of the representation and introduces the term projective representations. I take a quantum mechanical state, which is a wave function, together with all complex phases that I could possibly want to multiply with it, and I apply my symmetry operation onto this quantum mechanical state, and then I'm getting another quantum mechanical state with certain coefficients. So now these coefficients are only defined up to a complex factor. This type of a relationship, which really talks not about rotating a wave function, it talks about the rotation of a quantum mechanical state that belongs to that wave function. That is called a projective representation, because the projective representation takes into account that the quantum mechanical phase cannot be determined. So then you might also turn this argument around. Some people try to say, well, what does this, how can I determine this undetermined quantum mechanical phase? The existence of the spin tells us that we can never determine the quantum mechanical phase because we're asking the wrong question. If we could determine that phase, there would be no spin. So I've explained what that word projective means. Projective representation means that the phase is undetermined. The next thing I want to explain is compact. How many of you have had a course on topology? Okay, very good. 2, okay, very good. So since we were in the math department the first year in Regensburg, more than we were in the physics department, many of us took a course on topology. So the word compact is a term that comes from topology, and you can think of it as being closed and bounded. If you can build a very large box and you can put your quantum mechanical system inside that box, then that means that it is compact. And here are a few examples of compact spaces. There is the sphere, the torus. This is sort of like a double torus. This is a very strange bottle. It has a hole here at the bottom and the liquid goes in like this. So this is known as a Klein bottle. This is the Möbius strip. So you take a strip of paper, you cut it in half, twist it. And you can probably see that this Möbius loop, if you go around once, then if you have a vector pointing out of that loop and you go around by 360 degrees and it flips, it shows the other way. But if you go around twice, then you go back the same way. So obviously 720-degree rotations, that's something that we've heard of as physicists, that has to do with the spin. So compact is probably something that we can understand even if we don't know anything about topology. Connected is also something that we can understand. This topological space consisting of the green material, of the green blobs, that is obviously not connected. If you take out your phone and you type in directions to Las Cruces, New Mexico, your phone will tell you that it didn't find any a road to drive to New Mexico because Europe and the Americas are not connected. So this is a space, topological space, which is not connected, but all the others are connected. This red space here is obviously connected. This pink space and the yellow space are also connected. And this space D here, the brown one, this is also connected. So connected we can also understand. Simply connected, to understand simply connected is much harder. If we look at a sphere, then we can have a path on that sphere. So a loop is a path which ends up in the same point. So this is the point where we start and we go around once. And we can continuously deform. We can continuously deform this loop into a point. And you can see that we can move this. And topology is all about changing the shape without changing the class. And then at the end, we have deformed this path into a point. So a simply connected topological space, a topological space is called simply connected if every closed loop can be contracted into a point. And now here something happened to my figure. There used to be a torus here. So, as you can see, the torus has a hole in the middle. And if we start here at this point and we go around once, that path cannot be contracted into a point, and therefore the torus is not simply connected. Similarly, we can also go around this way, and the torus, and that path can also not be contracted into a point. So the torus is not simply connected, but the sphere is. The fundamental group classifies the paths that we can have in a torus. On a sphere, the fundamental group is trivial because every path can be contracted onto a point. But in a torus or in a circle, we can go around n times. So the fundamental group tells us how often we have to go around here. So if we go back here, then this space is simply connected. But this space C here, it has a hole in the middle. And that is not simply connected because the fundamental group tells us how often a path has gone around this hole. So why did I put this Carlo-Vivari cup onto the picture? This is topologically non-trivial because it is not simply connected. This cup here, the interesting feature is that this handle here is also a straw. So you fill the water in here and then you suck it out here. But in this cup, there's a hole here at the bottom, but there's another hole up here. So therefore, this is also an example of a topological space which is not simply connected. If we have a space, a topological space which is not simply connected, then we can find a covering. So imagine we have a pancake here, then a covering for that pancake would be an entire stack of pancakes. And I can project down, and locally everything looks the same. So that is a covering. So now, if I have a topological space which fulfills a number of conditions, then I can find a covering space which is simply connected. So even though the torus is not simply connected, I can find a covering space for the torus which is simply connected. And how do I do that? Well, first I cut here. And then if I cut the torus across here, then I'm getting a tube. And then I make a second cut along this direction, and I roll out the tube to get a sheet of paper. So this sheet is the universal covering group for the torus. Similarly, if I take a ring, I cut the ring, and I can bend it into a spiral. This spiral here is the universal covering group for the ring. In the case of SO3, it is not so easy to draw pictures, but mathematicians can prove that the universal covering group for SO3 is equal to SU2, and the fundamental group is the cyclical group with two elements. And that's why a 360-degree rotation flips the spin rather than leaving it invariant. But if I go around twice, I rotate by 720 degrees. The fundamental group is the cyclical group of order 2. So after 720 degrees, I get the original spin back. So let's look at this theorem again. The finite dimensional projective representations of a compact Lie group, we're interested in the rotation group SO3, are identical to the representation of its universal covering group. The universal covering group is SU2. So the projective representations of SO3 are identical to the representations of SU2. So that means that because the spin in quantum mechanics is undetermined, I'm sorry, because the phase in quantum mechanics is undetermined, that's where the half-integral representations come from, the half-integral spins. So now let's look at the projective representations of SO3. We already know the normal representations with integral angular momentum. So angular momentum can be 0, 1, 2, and 3, and the number of states that we can put there are, you know, for L equal 1, I have 3 wave functions. For L equal 2, for a D state, I have 5 wave functions, and so forth. The basis functions are the spherical harmonics. These are the representations that we're normally dealing with. But the representations of SO3 are not the only projective representations. In addition, I need to consider those representations, the extra representations, which belong to half-integral angular momentum. So in addition to the regular representations, I also have these extra representations. And therefore, this SU2 is sometimes called the double group that belongs to SO3. Now, this is just regular quantum mechanics of the spin. So now we need to apply this to a crystal. The point groups have rotations. So these are the regular representations of a point group that belong to integral angular momentum. But in addition, if I want to look at fermions in a crystal, I need to find these extra representations which belong to half-integral angular momenta. So therefore, the gamma 1 through gamma 5, those are the 5 representations belonging to the group O. But then I need to look at the extra representations belonging to the double group. So the electrons in a crystal do not have representations 1, 2, 3, 4, 5. Instead, the electrons belong to the extra representations gamma 6, gamma 7, gamma 8, because they have half-integral spins. The other thing that happens in a crystal is that we do not have the full rotational symmetry, and therefore the states with higher angular momenta have to split. So let's look at this D state, which has 5 wave functions, and if I have full rotational symmetry, then these 5 wave functions will all belong to the same energy in the Bohr model. But in a crystal, let's say with cubic symmetry, these wave functions, because there's 5 of them, they need to split because there are no 5-dimensional irreducible representations belonging to the crystal. And then I can do the same for the XOR representations with a spin. And in a cubic system, spin 1/2 and spin 3/2, those will not usually split, but the states with higher angular momenta, they have to split into multiple irreducible representations. So the only allowed degeneracies that we can have in a cubic symmetry is 1, 2, 3, and 4. We cannot have 5-fold degeneracies or even higher degeneracies. Lowering the symmetry. So here I talked about lowering the symmetry from the full rotational symmetry of a hydrogen atom to the cubic symmetry of a crystal. But there are other ways how I can lower the symmetry even more. Some points in the lattice have the full cubic symmetry, but others have other Wyckoff positions have a lower symmetry. So some atoms may not have the full symmetry that the entire lattice has. The Brillouin zone center, the gamma point, has the full symmetry of the crystal because it only has the potential energy. But once I add the kinetic energy that comes with moving away from the zone center, then I will ask for what is the group of that wave vector, and that group usually has the group of K usually has a lower symmetry than the entire symmetry of the crystal. And I can also lower the symmetry by applying an external field or by lowering the symmetry of the crystal. For example, if I go from a cubic diamond structure to a Wurtzite structure, so gallium phosphide, this is the phonon band for gallium phosphide. Gallium phosphide is cubic, but zinc oxide is Wurtzite. And therefore, this 3-fold degenerate phonon, which can vibrate either along X, Y, or Z, that phonon splits into a singlet or a singlet and a doublet in the Wurtzite structure. So the translational symmetry gives us the Brillouin zone. And if we add the kinetic energy of the electrons to the potential energy, then we get these band structure diagrams, which tell us about the relationship between the energy and the crystal momentum of an electron. You can think of this as a velocity, you can think of this as a momentum, but it's not really a momentum, it's a crystal momentum because of the periodicity of the lattice. You see that the X point in the diamond structure is always doubly degenerate. And that has to do with something that comes from the space group, not from the point group.
So sometimes to understand the band structure of a material, it is necessary to consider the representations of the space group, because the representations of the point group are not sufficient to explain the band structure. Also, as we compare the band structures of silicon and germanium, we see that for germanium, we have used the extra representations to describe the band structure because of large spin-orbit effects. We talked about the different band structures of germanium and alpha-tin in the first lecture, and I would like to emphasize a few points which make these materials different, where germanium is a semiconductor, whereas alpha-tin is a topological insulator. So first, if we look at germanium, then we see that along the delta direction, the gamma 7 minus and the gamma 6 minus bands cross. This is an actual linear crossing, so there's a Dirac point there rather than an anti-crossing like we might have in other materials. So the reason we have a crossing rather than an anti-crossing is because the two bands, the S and P antibonding bands, have different symmetries, and therefore they must cross and cannot be influenced by each other. If we look at tin, on the other hand, then we see that the S antibonding bands, the S antibonding band has moved between the P band manifold, between the split-off hole and the heavy and light hole bands. Therefore, we have a parity inversion, first P, then S, and then again P, and that parity inversion makes the tin a topological insulator. Group theory also allows us to determine selection rules for matrix elements. So the question that we ask here is if the initial state has a symmetry gamma I, and the final state has a symmetry gamma F, and the symmetry of the interaction Hamiltonian is gamma H, then is the matrix element describing a transition from I to F with this Hamiltonian allowed? And the answer to that is that the transition is forbidden unless the symmetry of the final state is contained in the product of the representations of the initial state and the Hamiltonian. That calculation is easier than it sounds if we refer to the relevant character tables. So to summarize this talk, we have discussed the various symmetries that can occur in a crystal. We have described the Wyckoff positions, which give us the atomic coordinates within each of the cells. We have introduced the Bravais lattice, and we have drawn the Brillouin zone, which allows us to work with plane waves inside a crystal in reciprocal space. We've labeled the symmetries of the electron wave functions, and we've looked at the band structure of a couple of materials, and we've seen that when the symmetry of a crystal is reduced, then this leads to crystal field splittings. We've looked at symmetry and group theoretical methods to describe the infrared and Raman active phonon modes in crystals, and we have looked at a variety of other selection rules in X-ray diffraction spectra.